All right, let's talk about another place where you could have a possible point of discontinuity. So we just talked about holes, remember removable discontinuity. But what about vertical asymptotes? When we have a rational function, we could possibly have holes, but we could also have vertical asymptotes. Vertical asymptotes are what we consider non-removable or infinite discontinuity, because you can't just plug it up with one value, right? Non-removable discontinuity is what we call vertical asymptotes. After identifying any holes, vertical asymptotes can be found by determining the value of x that makes the denominator equal 0. So after getting rid of your holes or identifying where your holes are at, putting your function in most simplified form, is there any factor that's going to cause that denominator to equal 0? Remember, we're not allowed to divide by 0. That's undefined, right? Let me show you an example. In example number 3, it asks us to identify all points of discontinuity. So removable, holes, or non-removable, vertical asymptotes. What is the value of f at these points? And what happens as we approach these points? I'm starting to put some notation you might have noticed in each question. You'll start to see these notations back when you take calculus next semester. But we're going to start talking about limits. What happens as we approach these holes or these vertical asymptotes? Okay? All right, in example number 3a, we've got an f of x. If I'm looking at this f of x, is it in most simplified form? Well, hopefully you recognize that you can factor not only the top, but you can also factor the bottom. So pause the video, take a second, and please factor both the numerator and the denominator here of f. Hopefully you recognize that the numerator is a difference of cubes. You remember your cubes factoring formulas. And when you factor, you end up getting x minus 3 times an x squared plus 3x plus 9. The denominator is a difference of squares, and you should be able to factor it into factors of x minus 3 and x plus 3. So now that I have my function into all little pieces, into little factors, do we have any points of discontinuity? Let's start first with holes. Do we have any place where we have a factor that's the same as the top and the bottom? Hopefully you recognize that there is a hole in this graph. It looks like there is going to be a hole at x equals what? Positive 3? Beautiful. Now, I've gotten rid of all of the holes. I have two factors left, the factor on top here, the factor on bottom here. So this would be a new function. That's the same picture as the original, just without the hole. But we also still have a factor left in the denominator. And what x value could cause this denominator now to still equal 0? At x equals negative 3, right? And so what that causes is a vertical asymptote. We know in our graph now that there's not only a hole at x equals positive 3, but there is going to be a vertical asymptote at x equals negative 3 in our graph. We have removable discontinuity and non-removable discontinuity. Okay? The second part of the question, what is the value of f at both of those points? If you remember back in our last example, if x equals 3 is a hole, when we plug 3 into our original function, what should we get in our numerator and our denominator? Well, if you plug 3 into the top, you plug 3 into the bottom, shouldn't you get 0 over 0? Remember, anytime we have a hole and you plug that value in, you should end up getting that indeterminate form, 0 over 0. We know there's a hole there. But what's happening at x equals negative 3? If you plug in x equals negative 3 to your function, what happens? Well, if I plug in negative 3 to the top, I end up getting negative 3 cubed, which is a negative 27, over negative 3 squared minus 9. So I end up getting 0 on the denominator, but I actually end up getting negative 54 on the top. And anytime I have a number divided by 0, it is undefined, which should kind of make sense also. When I have a 0 over 0, it's indeterminate. There's a hole there. If I have a number divided by 0, it is undefined. We have a vertical asymptote. There is a huge place of discontinuity at that vertical asymptote. If you imagine what the graph looks like, I know that as I approach that vertical asymptote, what's going to happen? Right? So that's the third part of the question. What happens as we approach this vertical asymptote, this c value, this negative 3? Well, imagine as you're approaching this vertical asymptote, as you're coming from the left, your only options are either to go up or go down, right? Same idea from the right side. As you approach this vertical asymptote, our only options are shoot up or shoot down. And so when we talk about approaching the limit as x approaches -3, as we approach that vertical asymptote, our function value, our y value, goes either up to positive infinity or down to -infinity. Okay? All right, let's look at B. Pause the video. Try looking at B, find me all the places of discontinuity, figure out what the function value will be at those places, and what happens when we approach those places. All right, hopefully you factored f. I factored f numerator into an x plus 6, x minus 2, denominator into an x minus 4, and an x plus 3. And so looking at this, where do we have holes? Well, it actually looks like there are no holes in this graph because there are no place where the numerator and denominator have the same factor, right? So on this graph, there will be no holes, but what will there be? It looks like there are 2 places in the denominator, 2 x values that could cause that denominator to equal 0, which means we have vertical asymptotes. We have non-removable discontinuity at x equals -3 and x equals +4. So if you imagine what the graph might look like, I know that there is no holes, but there is going to be a vertical asymptote at -3, x equals -3, and x equals +4, right? All right, so if I plugged in -3 to my function, or I plugged in +4 to my function, and I know there's vertical asymptotes there, what should I end up getting in the numerator? What should I end up getting in the denominator because of that vertical asymptote? Hopefully you didn't say 0 over 0, because 0 over 0 means I have a hole. We don't have any holes, remember. We have vertical asymptotes. If I plugged in -3, I ended up getting a -15 over 0, which is undefined. That's what symbolizes that we have a vertical asymptote there instead of a hole. If I plug in a 4 to f, I ended up getting 20 over 0, again undefined, which again symbolizes that we have a vertical asymptote at x equals 4, not a hole. We have non-removable discontinuities. All right, so what happens as x approaches -3? As we approach the vertical asymptote coming from the left or from the right, my only options are to go up or down. What about as x approaches 4? As you approach that vertical asymptote at x equals 4, what are your only choices if you're a graph? You can't touch the vertical asymptote, so you either have to go up or down. So again, as x approaches -3 or as x approaches +4, f of x, your function, has to go up to positive infinity or down to -infinity. So the limit as x approaches these vertical asymptotes are either positive infinity or -infinity. We're going to continue talking more about that in calculus, but hopefully this notation and these words, this vocabulary gets you ready for the things that you're going to do in Calc 1.